without further ado, please help me welcome James and Georgi.
Cool. Thanks, everyone. So I'm James, and this is Georgi. Right, let's get started. So, quick agenda. So we're going to run through our motivation for writing a kernel fuzzer. We'll go over our architecture, some caveats to be aware of if you're doing your own kernel fuzzing. We'll run through Windows as a case study, plus the other operating systems we've looked at. We'll run through the results we've got and what we're looking to do over the next few months. So, motivation. Typically now with sandboxing, kernel exploits are becoming more of a necessity. It's quite hard to break out sandbox environments, particularly if you're looking at things like Chrome. So if you look at the last pwn-to-own wins over the last few years, they've all used kernel exploits to break out the sandbox process. So yeah, kernel exploits, pretty important nowadays for things like privesc. Also at MWR, we have a bit of a friendly internal competition going on. So Neil's presented on his version of his Windows kernel fuzzer at T2. Obviously, we're trying to beat the number of bugs that he got in his version. But obviously, we're primarily here to try and improve general operating system security. Initially, and most of our research has been focused on Windows, Windows 7, but we've actually ported the fuzzer to run on OS X and QNX. And we're looking to start running it properly over the next few months and trying to find some bugs in those OSs as well. So, how hard can it be? If you look over at Twitter, it would appear everyone has Win32 KO day. And so do we. So, about a month ago, we did a run, purely a test run to make sure the fuzzer was pretty stable. So, as you can see, 16 VMs, just 48 hours. We got 65 crashes, 13 of those unique, which, yeah, I didn't think was too bad. 13 no days in Win 7. Okay, cool. As it turns out, though, we weren't being particularly effective with our fuzzing. So for those that don't know, there's a number of syscalls in Win 7 that are simply just sleeps for all intents and purposes. So we've got the one there, NT delay execution. So we managed to find that one, blacklist it, and actually, surprise, surprise, the fuzzer was a lot more effective. So we ran it again last week. We haven't triaged all the crashes, which is why we've not spoken in the slides, but we ended up with around 150 crashes, and 40 of those were unique. In the end, actually, we crashed our database. We were pushing all these crashes to because it ran out of space for it. So that seems pretty cool. We are going to release the framework for the fuzzer. So the core will be released, but we're not going to release any OS-specific stuff. But throughout the talk, we're going to go through how you would write the OS-specific stuff and give you some examples so you can go away and fuzz the OSs yourself. It's worth bearing in mind when you look at the code that we're hackers, not developers. It's pretty dirty in places. So yeah, bear that in mind. Our sort of test is, does it compile? Great, it probably works then. So, the architecture. Everything is nicely decoupled. So you've got in there the center of the framework core, which is basically what runs everything on the outside there, which is the OS-specific stuff. Originally, we devved this up in Python, but we've completely rewritten it in C. It's much more efficient, significantly faster, and seems to be finding a lot more bugs for us. So the first part is the OS API knowledge base. All this is the OS-specific API that is used by applications to interface with services provided by the OS. So this is the things devs do to, do things with graphics or interact with devices or do networking, etc., etc. Many of these will wrap system calls. We'll provide 2 examples of how we've devved these for Windows and OS X later on in the talk. But we won't be releasing all of our ones. The next major part of the OS-specific stuff is the system calls. So system calls are a low-level method for user space to kernel space communications. These have to be implemented per architecture and operating system. So that's fine for open source systems, OS X or any Linux-based system. These tend to be open source. For Windows, it's a little bit more difficult. You have to reverse engineer these ones out or rely on other sources, maybe React OS or something like that. At the bottom there, you can see what a syscall looks like internally to the fuzzer. So we just have a syscall ID, the arguments for that syscall, and then just a return data type if the syscall provides a return. Also, we have a number of fuzzed values. So there you can just see the fuzz values you can grab internally from the fuzzer. We use the words fuzzed, but what we don't necessarily mean fuzzed, actually. So really, we actually want the library calls and syscalls to work, and to get these to work, we actually have to return proper values. So whilst we occasionally return a properly fuzzed value, most of the time you'll return a normal value that is going to ensure that the library call and system call works. Yeah. So the next part is the object store. The object store is used to maintain state across a fuzzing run, and it stores OS-specific objects of interest. So currently, this is handles in Windows and file descriptors in Linux systems. It's implemented as just a global array of structures. It's deterministically populated by the fuzzer, and this is quite important for when we want to reproduce crashes. If this wasn't deterministic, then obviously we'd just never be able to reproduce any crashes we found. It's quite easy to retrieve, update, and insert new objects into the object store. Okay, the next bit is the helper functions. So helper functions, we use these for things like library calls that require a struct. It works in pretty much the same way as grabbing a fuzzed value. So if you want to call for a struct for a library call, you make a call to the helper function, and it will return you a struct that should be or should work fine in the library call. So logging. This is actually quite difficult in kernel fuzzing when you keep hitting crashes. So initially, we didn't have high hopes for the fuzzer, so all we did was log a PRNG seed. As you might guess, as a fuzzer, we make heavy use of the rand function. So if we can just seed this again, we'll always get a same run again, which makes reproducing quite easy. Bit of an issue, though, is it doesn't generate a standalone test case, which is ultimately where we want to get to. So what we've moved on to doing is logging C statements. So our log files are actually complete source files. And all we do is copy and paste these into a template. There are some issues with this. So occasionally, if we get a BSOD, we'll find that actually the OS hasn't flushed the write to the file before it's BSODed in the Windows instance. So we miss out on, let's say, the last call. As a workaround, what we're doing is we're usually able to grab the stack trace and the arguments and everything else and figure out what it was doing. What we're looking towards doing in the future as well is maybe using something like logging over a socket or something like that, which we're hoping will work a little bit better. As you might guess, this is incredibly tedious. So this is an example of our logging from a library call. What we do is we grab a variable ID to tag onto the end of a variable, and then we assign that variable and call a function. As you can see at the bottom, we log the function call before calling the function in the fuzzer to try and ensure that we log the crash before it actually crashes. So, crash detection. There's actually two methods we tried with this. So the first way we tried was just attaching a kernel debugger while we were executing the fuzzer. Obviously requires one or more debugger processes, which slows execution. So you can either have on the host debugging the VMs or a VM debugging another VM. But the plus point is we instantly analyze any crashes we find. The other option is unattended execution, which is what we're working on at the moment. And this is just letting the OS handle the crash on its own. Much faster execution, and we can run more VMs as well, and we have less wasted CPU cycles. We recover and analyze the crashes upon reboot. Another way we've been looking at actually is using hypervisor logs. So for example, VMware will actually log when a host has crashed, and there's some information in there that is actually quite useful. So this is the way the logging, the crash detection, works. When we reboot the box, the first thing we'll do is try and search for memory dump files. So this is quite specific to Windows. If we find a memory dump file, we'll match that up with a log file. So there should only be one log file on the disk, which is the one that caused the crash. If we get that memory dump file, what we do at the moment is under WinBag, bang analyze, and just grab those details out. And then the three of them, we timestamp and just archive them all off. So with a number of VMs, so our ultimate goal is to run this across hundreds of VMs, is we need some form of way of the fuzzer to push this into a central database. So those three files I just described are actually pushed into a CouchDB database, so we just have sat in AWS. This is really useful for us because it means we can actually do deduplication across all the VMs. So all we do is hash the stack. If we've seen that hash before, we just drop the files and increment a counter. If we haven't, then we push the files up into CapsDB. It also means we can do some other categorization stuff, so doing stuff like type of AB, faulting IP, bug check ID, etc. Closer to the mic. Okay. Okay, so that's the overall architecture for the fuzzer. Shall I unplug it? Oh. Right, yes. So that was the overall architecture. So this is what a fuzzing run looks like. The first thing we do is we have a little bootstrap script that we run to prepare a VM for fuzzing. It's just a really simple Python script. It installs everything that's required and just fine-tunes the system. So we'll go through what the Windows one of that looks like later on in the talk. We then launch a second Python script, which is a wrapper around the core fuzzer. But what that one does is go away and collects the memory dumps and submits it to the database if it finds them, et cetera, as I just said. We then launch the fuzzer binary, and the first thing we do is populate that object store. So we generate a bunch of valid handles or file descriptors that we can then use for library and system calls straight away. Okay, so then for a predefined number of iterations, we pick up either a library or system call. So we'll go away, figure out what the arguments are, and then grab either fuzz value, fuzz struct, or an object from the object store. And then we invoke that call. We check to make sure it's succeeded, and if it gives us a value back that's useful later on, we'll pop that back into the object store. So, you know, library calls or system calls may return a hand or a file descriptor or something similar. And we want to keep hold of that value and use it later on. At the end, if we didn't get a crash, all we do is just clean up all our temporary files, remove the logs, and just try and revert back to a clean state. Now, currently, all we do is reboot the box. So this should mostly give us a clean state to work from for the next fuzzing run. Obviously, we can't just start the fuzzer again, because if we have done something in a previous fuzzer run that we haven't logged, it's impossible to reproduce that test crash, and it's useless to us. We're actually also looking at how we can possibly revert back to a VM snapshot, as this will guarantee a clean slate to start from. A few caveats to be aware of if you're going to take this framework and use it yourselves. We found a number of bugs in the hypervisors, which has meant we haven't placed this up in the crowd. I'm pretty sure people like Amazon will get really annoyed with us if we start crashing their hypervisors. So what we're looking at doing is running it under QEMU, which is a bit inception-y, but should hopefully work. You also need to look into things like, we're also looking into things on how to protect the fuzzer from itself. So on a number of occasions, somehow the fuzzer has managed to get a handle to itself and kill itself, which is kind of irritating. So what we're trying to move on to is a method of how we monitor the host that's fuzzing, monitor the guest, from the host. So if the fuzzer's killed itself, or we've hit another sleep or done something else stupid, we can detect that and then start the fuzzer off again. Cool. So I'm actually going to hand over to Georgi, who's going to go through Windows case study.
As James already mentioned, we initially started with the idea of developing a Windows kernel fuzzer. And this actually remained our focus despite of repurposing the fuzzer for OS agnostic operations. So the second half of the talk is dedicated on getting the fuzzer working efficiently on Windows and basically writing all of these custom modules for the Windows operating system. So all of these operating system tweaks and object store implementation details that you need to consider when you take the framework and you want to basically use it for fuzzing Windows. I'll be going through several examples for each one of these bullet points. So basically examples on how we implemented our object store, some examples on what our collection of system calls looks like in Windows, and basically some examples on the wrappers for the library calls that we have developed. I will be ending this with basically what's the process of bootstrapping the Windows VM before we actually start fuzzing. So the attack surface we decided to focus on is the Win32k subsystem, a pretty well-known attack surface in the Windows operating system. This subsystem implements mainly three components. The window manager, responsible for desktops, windows, menus, toolbars, the general user interface elements, and the graphics device interface, also known as GDI, which is in charge of visualization on the screen, changing colors, and basically just general graphics. Win32k.sys also implements some wrappers for DirectX calls, and this is not something we have looked at until now. And this is probably not something we'll consider in the future. There is counter components in userland in terms of user mod libraries, a bunch of DLLs provided for application developers to actually interface with the subsystem. So if you're an application developer, you wouldn't issue a syscall to the win32k.sys kernel mod driver. You would be going on SDN and looking at how you interface with this kernel mod driver using some library calls that will eventually wrap into a system call. In the Windows operating system, an object is basically a data structure representing some sort of system resource, and this can be anything from file, process, window, menu, etc. There's roughly three main types of objects in the Windows operating system: user objects, GDI objects, and kernel objects. User objects are implemented to support the window manager. Obviously, GDI objects implemented to basically manage the graphic device interface, and kernel objects are basically there to implement basic operations in the kernel space, such as process management, memory management, IPC communication, etc. One important thing to realize when we talk about object is that when an application wants to manipulate an object, when an application wants to access an object, it needs to acquire a handle to that object. So if you want to do something with any of the system resources, you need a handle to each one of them in order to basically interface with them. And this is how handles are defined. Object handles are defined in the Windows SDK on a really, really low level. They're just basically void pointers managed by the operating system. Now, the implementation details are hidden from the application developer, and the application developer shouldn't really care about how these handles are implemented. And this is just here for a reference. Furthermore, numerous aliases are defined for more or less any system resource available on the operating system. So this is a snippet from windev.h, header file from the Windows SDK, where a bunch of these declarations actually happen. There's declaration to a handle for a handle to a window, declaration for a handle to a bitmap, etc. So each one of these system resources will have a sort of specific handle associated, a handle type associated with it. So knowing and realizing how fundamental object handles are in the Windows world, it comes as no surprise that we actually decided to preserve object handles in our object store. The object store implementation itself is really straightforward at the moment. It's just a globally accessible array of 120 elements where we just preserve a bunch of handles to numerous system resources. Handles are retrieved from this object store when we need a handle to be passed as an argument to a system or a library call. And should a system or a library call return successfully another handle, we consider this handle and we push it back to the object store. Sorry. If we start running out of, let's say, space in our object store, in this case, it's a fixed value of 128. Let's say we start running out of slots in this array, we basically start overwriting some of the handles from the object store. We basically throw out the oldest handles and we repopulate the object store with some new ones. One more thing to basically notice is the BH handle struct. The BH handle struct is our internal representation of a handle. It has two fields, which is the handle itself, as well as the index of the handle in the object store. So handles will be changing values per run. So basically, if we grab a handle to a particular window in one run, this handle will have one value. If you grab a handle to an identical window in a second run, this handle will have a different value. So how we grab the same handle twice, by basically referring to the handle not by its value, but by its index in the object store. Excuse me. We have implemented a number of functions to interface with the object store I'm talking about. The first one is basically there to bootstrap the object store, populate the object store with some handles before we even start fuzzing, so we can actually use some handles as arguments for library and system calls. The second one is the function getRandomHandle. This function will basically look up the store and randomly pick up a handle from it. It will then wrap the handle in a bhhandle struct, which helps us successfully log the location of the handle in the object store when we issue logging statements. We have another function for querying the object store. This one is getSpecificHandle. This one takes one argument, which is basically the index of the handle we want to extract retrieve from the object store. We also have a function for inserting handles back to the object store. Again, should the library call return successfully a handle, we just push it back to the object store. For populating the knowledge base of system calls, well, basically for the majority of them, we had to reverse engineer them. We started with mainly system calls implemented in the Win32K subsystem. But there's one thing, when I say reverse engineering, I don't really mean reversing the logic of the system call itself or how the system call is implemented under the hood. The only details we're interested in are basically the system call ID, the number of arguments for the system call, and the data type for each one of these arguments. Optionally, again, the return type for the system call. So for the majority of the system calls, you have to do some reverse engineering. For some of them, you may also refer to ReactOS, but this is not necessarily identical to the Windows revision you're working on. To implement the syscall invocation itself, we had to write some assembly snippets, and these are specific to both the operating system and the architecture. A little bit more about the assembly snippets in just a second. This is what an extract from our collection of system call looks like. James already mentioned what our internal representation of a system call looks like, the syscall struct. The syscall struct has got 3 fields. The first one is the system call ID. The second one is an array of data types for each one of the arguments consumed by the system call. And the third, an optional field, is basically whether the system call returns any data type we may be potentially interested in. The system call invocation, again, is implemented per architecture and per operating system. We have what we call system call invocation template. The prototype for the template is the same across the architectures. And this is the call with the name buckhan_syscall. This function, this template function, takes 33 arguments at the moment. The first one being the syscall ID, and the second, basically the rest of these 32 arguments are arguments for the system call itself. Now, obviously, not every system call would be taking 32 arguments, or I don't even know if there is any system calls taking 32 arguments at all. The reason we did a fixed number of arguments is because we didn't want to implement a function with a variable number of arguments, a sort of printf-like style. So what we do at the moment is we set the system call ID as the first argument for this function. We populate the first argument with the actual data that should be passed to the system call, and we just pad the rest of the 32 arguments with some dummy data. And then buckhan_syscall is in charge of setting the registers for the invocation of the system call, pushing each one of these 32 arguments on the stack, and then making transition in kernel len. Once we're in kernel len, the system call is in charge of basically dispatching the request, taking care of each one and processing each one of the arguments that are actually expected by the system call. The system call will then simply ignore the rest of the 32 arguments on the stack, the system call will eventually return back to the backend syscall wrapper. Backend syscall wrapper will clean up the stack and return to the main fuzzing loop. This is just a general reminder on how system call invocation works on Windows. For x86 platforms, we have arguments pushed on the stack in a reverse order. We have EAX set to the system call ID, and then a call is made to the ki fuzz system call function. And now there is a caveat. This is basically this is the case until Windows 7, which is the operating system we have been mostly focused on. I think in Windows 8 and Windows 10, the ki fuzz system call has been basically inlined in the code. For x64, the first 4 arguments are set in registers. These are RCX, RDX, R8, and R9. If there's any additional arguments that are pushed on the stack, then RAX is set to the system call ID, and the CPU instruction syscall is made to basically force transition into kernel space. So much for system calls. Now, several examples on how to implement the OS API knowledge base. The OS API knowledge base, the information that we need for it is publicly available on MSDN. These are basically the library calls that, again, application developers are expected to be using when making requests to the operating system. The OS API calls knowledge base is implemented as one huge array of function pointers to each one of the library call wrappers that we have implemented. I think until a few days ago, we had about 500 library call wrappers. So basically 500 functions from GDI32.dll, user32.dll, and some other user mod components. As you can imagine, this is a really tedious process of implementing wrappers for each one of these. We looked at automating this by basically crawling MSDN, collecting function prototypes, and turning these prototypes into library call wrappers in a more or less automated way. But unfortunately, we felt miserably with that, and we're looking forward to basically improving our approach. But at the moment, again, each one of these are implemented strictly manually. I'm going to give a few examples now. This is the destroy caret function from MSDN. This function takes no arguments and returns a Boolean value. And the wrapper for this call is really simple, really straightforward. Basically, we log the code that we're about to make, and we make the actual call. That's literally it. So in the log file, we basically end up with the exactly same C statement that we're making in our fuzzer. Something a bit more interesting is the following one, destroy cursor. On the top, you have the prototype from MSDN. This one takes a single argument. This argument is basically a handle to a cursor object, and this function returns a Boolean again. So what we do in our wrapper, we declare the handle, but not as a handle. We declare it as a bhhandle struct that wraps the handle itself as well as the index. We generate a globally unique variable ID that will be appended to the variable name when we make a logging statement. We then log the declaration for the handle while appending the variable ID to the end of the name of the function. We proceed by grabbing a random handle from the object store and assigning it to the handle that we are going to pass to the library call function. Then we log the handle, we log the handle by its index rather than by its actual value. And James mentioned this, but the object store at any point of the fuzzer run is populated in a deterministic way, at least in theory. So if we're up to a point where we know the object store has certain handles, we can refer to each one of these handles by its index, and it should be the case of getting the same handles that we got the last time we run with the same seed. The last thing we do is basically log the final call that we're about to make. This is the actual call, the actual library call, we log this with the respective variables, and while again appending the variable ID at the end of them. And then again, the last thing is just simply make the call. something a bit more interesting. So, for example, this example demonstrates how to use the helper functions. The helper functions are functions that will generate a valid struct, a Windows-specific struct that is consumed by a library or a system call. And I'll be talking about the helper functions in just a bit. But basically, this is a function taking two arguments, a handle to a device context, and a colorref Windows type. We start with the same thing again. We declare the variables that we're going to use within the wrapper. We generate the variable ID. Again, this will be globally unique across the run. We log the handle. Again, notice that we log the handle as a handle, not as a BH handle. We basically hide the implementation details for a BH handle when it comes to the reproducer test case. We grab a random handle, assign it to our variable. The next thing is log the handle by its index, and the next thing is the interesting bit where we actually make a call to a helper function. This one is get colorref, and each one of the helper functions takes a single argument, which is the variable ID. So get colorref will basically hide the details for us, but it will populate with mostly valid data again this struct that can later on be used by our library call. And again, the last thing is log the statement, log the code that we're about to make and make the actual call. And now a bit more about the helper functions. There's just an endless number of custom structs in the Windows operating system, and they are expected by a number of library calls and system calls. And this is where the helper functions come. Basically, for each one of these, well, obviously we cannot implement for each one of them, but for the most common ones consumed by the Win32K system and library calls, we have implemented helper functions. So basically, we have helper functions for returning rectangles, points, sizes, windows, etc. And again, these are mostly valid, and they shouldn't really be way too malformed. At the bottom of the slide, you can basically see a snippet from the list of helper functions we have implemented. Again, the helper function will return a valid struct. The naming convention is get underscore name for the helper for the struct, and the single argument that will be consumed is the global unique variable ID. This one is really obvious and really easy to implement because this is just a typedef word in Windows. So basically, we start by declaring the colorref variable. We log the declaration by appending the variable ID to the name of the variable. We initialize the variable by calling get underscore first underscore uint32. This will basically grab an unsigned integer from the first value store, assign it to CR, and then we log this value as it was assigned and return the struct to the caller, which will be then passing this struct to the library call. Something a bit more interesting. So, for example, this one is a helper function for returning a rectangle. Rectangle is a struct with 4 fields, each one of them of type long. So what we do is basically pretty much the same, apart from initializing each one of the fields separately. And for each one of these initializations, we log in our log file. Case study, fuzzing the Windows VM. What do we need to do in order to basically get a decent VM, basically the VM in a decent state for our fuzzer to run in an optimal way? We start by installing Python 3.5, and then we have a bootstrap script that will set up the VM and do some general OS tweaks. This includes installing WinDebugger, installing the Python module for CouchDB communication in order to submit our crashes to the centralized database. We perform some minor tweaks in the registry, including disabling error reporting, disabling updates, etc. We enable kernel memory dumps. Basically, this is where we get the information about the crash. We enable spatial pool for the module that we're fuzzing, for the kernel mode driver that we're fuzzing, which in this case is win32k.sys. A spatial pool is basically the equivalent of page heap in kernel length, and a spatial pool will make it a lot easier to detect use after free vulns, double free, and some general pool corruptions as well. So it's very important to enable this. And the last thing, and obvious thing, is to schedule the fuzzer control script to start on logon and reboot the system. Upon rebooting the system, the fuzzer kicks in. The first thing to do is look up the location for where we store the memory dumps. So if there is a memory dump, we grab the memory dump, we run bang analyze using ktexe. We store this in a log file that will later on be submitted. We checked for a leftover fuzzer log from a previous run, and we basically assume the fact that this is the log file that caused the last BSOD. We bundle everything together, which is basically the fuzzer log, the memory dump file, and the output from bang analyze, and we submit all of these all together to CouchDB, where CouchDB will in CouchDB we'll be able to do some triaging and querying based on the crash. That was pretty much about it. When it comes to Windows, again, we have done some stuff on Mac OS X and QNX just to prove the concept that it actually works and the fuzzer is more or less platform agnostic. We haven't really spent too much time fuzzing Mac OS X and QNX, but we've got some again, prototypes for it. When it comes to system calls, in other operating systems, they basically follow the same calling convention, which is system v AMD64 application binary interface. And the object store for POSIX and Unix operating systems will store file descriptors most of the time, as opposed to handles. And file descriptors are more or less similar to handles, which is basically the most similar thing we can get to handles. And for the crash detection, we have both the same choices, either attach a kernel debugger or rely on the operating system to get some useful information for us in the syslog. This is just an example for a single function wrapping an IO kit library call. It's very much similar to what we do for Windows. The only difference is that we don't have handles, we don't have or Windows-specific helper functions. We have IO kit helper functions that will return an IO kit object when it's needed. Again, very much similar. When it comes to syscalls on Mac OS X, we're kind of lucky because the XNU system calls are all stored in a single file called syscall.master, and this file can even be processed in an automated way to extract all of these system calls with their IDs and their arguments, and basically turn this file into a collection of system calls that can later on be consumed by the framework. Some of the results James already mentioned. We're getting some interesting crashes in Word2k.sys, primarily in Windows 7. Why Windows 7? Well, probably because most of our users are on Windows 7, unfortunately. When it comes to other operating systems, again, we're looking forward to basically spending more time on there. The current implementation for Mac OS X specific and QNX specific modules is just a prototype, to be fair. We have some crashes in hypervisors, which is something that we never intended to find. So this is basically just an annoying thing happening at the moment rather than something we can brag about. We also found some interesting bugs in VMware tools and VirtualBox guest editions. Basically, these are vulns that may potentially be used for escalating privileges because VMware tools is obviously running with an escalated context. The setup that we're using, and this is just a setup for the stability runs, we haven't even thought about scaling it at the moment, mostly because we are satisfied with the results, is host operating system Win10, hypervisor, VMware Workstation, guest operating system Win7 64-bit, and the VM specs is pretty modest, to be fair, just 2 gigs of RAM and a single CPU per VM. This is just to recap the results from what James mentioned. Number of VMs 16, stability run for 48 hours, 65 crashes, 13 of them unique. And this is before we started blacklisting all of the syscalls causing a lot of problems. A breakdown on the type of crashes. We have 4 no-pointer derivs potentially exploitable in Win7. Fortunately for Windows, not exploitable on Win8 and Win10. We have some use after freeze, 2 of them. We have 4 pool buffer overflows, basically pool corruptions, and we have 3 under the category of miscellaneous, basically 3 invalid reduxes violations we haven't properly triaged by now. This is a breakdown on the crashes based on the bug check ID. The interesting thing here is to notice that a number of these crashes have been caught only thanks to special pool being enabled for the Win32k.sys kernel mod driver. So should you run without special pool, you end up with at least half of these crashes. Further work, what we can do to improve the framework and to improve the Windows-specific modules, for example. Obviously, we want to increase the coverage. How can we increase the coverage? The easiest thing, and what I think is a very efficient way of increasing the coverage, considering the current architecture, is object tagging. So if you remember, in the object store, we preserve a bunch of handles, but these are handles to any kind of object. So object tagging would basically involve adding another field in the BH handle struct, and this field will specify the object type for the handle where this handle is pointing to. So when we make a request to the object store, we will be specifying the type of object that we are expecting to find on the other side of the handle. We have, well, obviously we can implement more of these library calls. 500 is a good number, but there are so many of them we can implement. We have experimental implementation for user mod callbacks based fuzzing. This basically works at the moment, but we had some problems with the logging. So none of these results that I was talking about are with user mod callbacks enabled in our framework. So once we get this working, I expect even more crashes. Another thing is multi-threading. If you can imagine, the log file that we currently produce is a huge log file of C statements that are plugged into a main function and executed in sequentially, basically. So this is a problem with multi-threading. All of these runs have been from a single-threaded run of the fuzzer. Obviously, we have to work out how to implement proper logging with multi-threading at the same time. We can also look at some coverage feedback based on CPU features. So if you know about NCC's Triforce implementation, well, would it be possible to basically get something similar for Windows? Under miscellaneous, we're always looking forward to improving the logging, because basically it's just a really tedious and slow process of implementing each one of these library calls with the log statements for each one of the C statements that we have in the file. We haven't looked at handling hypervisor crashes at all. So basically, if a hypervisor crash occurs these days, we're just going to have to monitor the database and see that the number of crashes is dropping, and then we realize the hypervisor has been down for a few days. Test case reducer, we have considered looking at CReduce. This is a program which is basically a test case reducer, language-aware test case reducer that can successfully reduce C files. We haven't really implemented anything on top of that, but the basic idea is that one VM will be reducing the test case, will be feeding this test case to another VM. This second VM will be compiling and executing, and will providing feedback back to the first VM, which is constantly reducing the test case. And just in general, we definitely need to implement decent logging for the VM, and ideally this logging should be hypervisor agnostic. So basically this monitoring should be working on VMware, VirtualBox, QEMUs, and etc. These are the people we want to thank. These are all people who provided really valuable feedback and some useful ideas and information when we implemented the fuzzer. Basically, the core of the framework will be available online, I think, later next week, as soon as we get back to the UK, basically. And yeah, keep an eye on Twitter. We'll be bragging about releasing the framework, I guess. If there's any questions, I'm happy to take them at the cafe area, because I'm being told we're running out of time. But yeah, thanks, guys.